this could be overflow. Oh, okay, so we're going to do example 2 now. So we have a situation where there's somebody's getting their lungs checked out and they're exhaling air into a machine that measures lung capacity. Maybe you've had this done before if you have asthma or something like that. Okay, so the situation, the actual measurements here is 350 cubic centimeters of air, right? Cubic centimeter. A cubic centimeter is a milliliter, isn't it? So that's a volume of air exhaled from the lungs at a pressure. Okay, so that air is experiencing a pressure of 1.08 atmospheres at body temperature. 37 degrees Celsius is body temperature. So he puffs the air out into there, and the machine, though, is at different conditions. It's experiencing a room pressure of that and a room temperature of that. So the volume of air measured by the machine is going to be something different than what he is exhaling. So you certainly hope the machine is going to account for this behavior of gases. So let's calculate the volume of air measured by the machine. So how do we approach this? Well, we're doing something to the air. It starts here and then it goes into the machine. So we've got, like, in the body, we have a certain volume, pressure, temperature. That's like conditions 1. And then the machine, it's a different volume, pressure, and temperature, conditions 2. So what are we going to do with that? It's almost like we have to write PV equals nRT twice. If this is condition 1, how about we call this like pressure 1, volume 1 equals N. I guess the number of moles is the same here. R is the same, but the temperature is different, so T1. And then over here, we'll call this P2V2 equals NRT2. So we're not changing, we're not letting the air escape. It goes directly in the machine. So N remains the same and R is a constant. So we have 2 situations, N, same. And we're trying to figure out the volume of the air in the machine. We're trying to find out this one. So right there, V2 is what we're trying to figure out. So we have values for P1, V1, T1, P2, and T2. We don't have a value for N. So that's probably okay. Oops, sorry. But we do have a value for R. How about we do this? How about we say, let's bring that T1 over. P1 V1 divided by T1 is equal to NR. And then over here, P2 V2 divided by T2 is equal to NR. So both of these quantities are equal to NR. They're both equal to the same thing, so we can set them equal to each other. P1 V1 over T1 is equal to NR, but NR is also equal to P2 V2 over T2. This gives us a new equation. We just derived a new equation that helps us with a situation where we're changing the gas sample. So that's going to help us solve this. So we just got to do a little algebra to solve for V2. So V2 is over here, so we got to get T2 to the over to the other side and P2 to the other side. So T2 divided by P2 times P1 V1 over T1 is equal to V2. So then we just have to plug in the numbers properly in order to get our answer. So T2, what was that? Our T2, that's at the machine, and that's the 23, but we got to put it in Kelvin. So we got 296.15 Kelvin times the pressure P1, that's the body pressure, that was the 1.08 atmospheres. And the V1, 1 is body, so that is the 350.0 cubic centimeters, which is also known as mils. And then the P2 at the machine, 0.958 atmospheres. And the T1, body temperature in Kelvin. All right, so make sure you practice this and make sure you get the answer 377 cubic centimeters or mils. So the original volume of air exhaling is a 350, and once it goes in the machine's measuring more lung capacity. So you hope the machine is calibrated and realizes what it truly is. So that's example 2. Let's try another example. So example 3. All right, this time we have a diver. It says a deep sea diver is at a water depth of 100 meters below sea level. The pressure in her lungs is a lot. It's 9.7 atmospheres, and her lungs have a capacity, like a max volume of 6 liters. Uh-oh. How would the volume of the air in her lungs change if she were immediately brought to the surface? Instead of being below sea level, brought to the surface, assuming no change in her body temperature. So immediately, it's a quick, bring her up quick. It's probably not a good idea. I mean, she's probably going to experience the bends, but, you know, bends aside, let's see, how would the volume of the air change? So it's a change, so we're going to need this relationship of P1, V1, etc. We need this combined equation because we have this change. And we're trying to find out volume. We're trying to find out that V2 again. Now, temperature is not changing, so you know what? We could just leave that out. So we just have P1, V1 equals P2, V2. So V2 is equal to P1, V1 over P2. So the first pressure is 9.7 atmospheres. The first volume is filling the lungs, 6.0 liters. And then the second pressure, what's that? Oh, that's at sea level, brought to the surface. So that's 1 atmosphere, sea level. So we calculate this. Did you do it? Yikes, 58 liters. That is not good for this diver. Yeah, she would explode. Not good. All right, after we recover from this, try the last video.